Hey, this is Jason Kanigan from Cold Star Tech. I'm here with Dr. Rick Fleeter, our technical engineering advisor. And we're going to talk about something that, again, came up in a chat he and I were having the other day. And this is a weird thing. It's like, and I'm going to let Dr. Rick here talk about it because it starts off with Murphy's Law. So let's begin with that. Whatever can go wrong will go wrong was the mantra from the 50s going forward. And you've adapted that into something else for the current new space.
Well, I think we all kind of grew up in engineering thinking that Murphy's Law was the thing, that complex systems have a lot of failure modes. And I really think it all got started maybe with the ENIAC computer, which had who knows how many 100,000 vacuum tubes. And the amount of computing it could do was limited by how much time it would take for one of those vacuum tubes to die. And we don't live in that world anymore. I mean, we have, integrated circuits with, many orders of magnitude times more switches in them, and they never fail. And so what is the enemy nowadays is not that things aren't going to work or that whatever can fail is going to fail. It's more what I call the law of unexpected consequences. You have a lot of things that have a lot of capabilities, and you don't know how all these complex systems are going to behave in any given situation. And so the system is working perfectly, but it's not entirely predictable what it's going to do at any given moment. And that lack of Murphy's Law, the fact that everything is actually working the way it was designed to, but we're not smart enough, no one person really understands how the International Space Station works. And so, it's all divided up into little pieces. And so everybody understands their piece, but we don't really understand very well how the whole thing is going to work. That's the new Murphy's Law. Unexpected consequences are where our failures are coming from, and not, oh, this valve didn't open, or, this processor failed.
It's hard to predict that.
Very hard. And it's hard to predict it. I mean, we were talking about testing. The problem with testing is, sure, if you have an oscillator with 5 parts and you run it for 100 hours, you're pretty sure you know that it will work for 100 hours. If you have a part with billions of states that are possible, you can run it for a year and you really haven't even begun to see all the possible modes that thing can go into. And so our inability to kind of investigate all the possible states and see which ones of them might be dead ends is really more of our problem, not that things are not going to work.
Okay. What can people do to mitigate this kind of risk?
Yeah, well, that's a really good question, because I think the answer people don't like, which is, you got to take the time to actually run the thing in the situations that you're going to be using it in and see if it doesn't fail. If it does fail, it's not a Murphy's Law failure. It's a failure of going down a logical tree that people hadn't ever anticipated before. And then you have to debug that failure. So, given that we don't have the tools to investigate a billion trees, it kind of, unfortunately, the answer to a kind of a new problem is a very old answer, which, I was saying to you, in the old amateur radio satellite world of the 70s and 80s, we had the 1,000-hour test. Put the satellite in isolation, talk to it only with the radio, charge and discharge the batteries, put sunlight on it half of the time or 60% of the time, and operate it for a month and see if it goes into a mode you don't like that requires you to actually put your finger on it and restart it, because that's the thing you can't do in space. And if it runs for a long time and it's not messing up on you, then you have confidence. So we know we've run it through all of its paces. We've asked it to do all the commands that we're going to ask it to do in space. We've done a very interesting thing on a lot of our satellites that are delivered to other customers, which is we don't allow the customer to write a command line because it's too unpredictable. On your PC, they're kind of blocked. So if you type weird things onto the keyboard, the PC says, okay, he's typing weird things. We're not going to pay attention to this. So, we don't give the customer a direct line into the processor. We give them essentially a Macintosh type environment. Here's all the commands on pull down windows. You can put your commands together from these. Other than that, you can't generate. If the customer comes back to us and says, we want to do something that's not on the command line, we will do it on a satellite in simulation on the lab benchtop. before because of, again, this unpredictability of if we do that and we've never done that before, we don't know where it's going. So there are ways to solve it. There are definitely ways to solve it. But we don't think of that as the way we engineer because of our focus on, if the transistor is not going to fail, then I'm off the hook with Murphy's Law. But you are off the hook with Murphy's Law, but you still don't know how that person is going to react in that particular situation, or in this case, the satellite. But satellites are getting nearly as complicated as people now.
Now, I think, so two things come up from that in my mind. First of all, the squishing of the test part of the project in development and design and manufacturing. When every mistake or error or correction that needs to be made up front in the design phase takes away from the half to 2/3 of the schedule that really ought to be for testing on the back end. And you've mentioned, we need to talk about this at some later time, the political side of budgeting the project and people not liking, oh, why is all this money going into testing, right? Because they don't understand that's where the failures in orbit tend to come from, you know. So that's a compounding problem. And second of all, for a $5 billion satellite, sure, you're going to do the 1,000-hour test, right? That makes a lot of sense, but not, you know, as satellites get cheaper and cheaper, right? You're not going to do that with a $200,000 CubeSat, right?
There's this idea that, you know, I've fought this idea all my life that, oh, a small satellite is basically a throwaway. It's not a throwaway for the 6 people who built it. You know, they dedicated 2 years of their lives to it. So it's just, yeah, it all scales. A little satellite is 6 people, and a medium satellite is 600 people, and a big satellite is 6,000 or 20,000 people. But the rules of physics haven't changed because of that. And the only way to track down these failures of going down all the possible behavioral trees are, like I said, the way to solve it is by going down as many of the behavioral trees in advance, all of the ones you think you're going to use on orbit. You don't want to go someplace on orbit you haven't already gone on the ground, so you need the time to do it. And unfortunately, nothing is coming out of that time. When you have manufacturing time, the manager can say, oh, this box got built, this, you know, circuit board went through thermal vacuum and vibe testing. But when you're doing this kind of going down the tree testing, it's just a bunch of electrons moving around. Nothing appears to be happening, and there's no new product at the end. So it's massless, it's invisible, and therefore it's a little bit undervalued, I think.
This reminds me of the production possibilities curve in basic economics, the guns versus butter thing. It's a binary, right? You're either engineering and manufacturing and you know, moving the project along, or you've stopped that entirely and you're doing this testing thing, which unfortunately doesn't really pay off unless you encounter a failure.
Yeah.
And there is a diminishing returns, I guess, in putting effort in going down all these trees. So I wonder if data science will be, you know, Cold Star being partially a data science company, right? I wonder if data science will be helpful with unsupervised machine learning and finding out some stuff about.
Maybe in estimating how much time it's going to take based on the complexity of a system. Because those of us who are managing those problems have an intuitive idea of how much time we're going to need to get the bugs out in testing. But I think data science could help us by saying, with a system of this complexity level, using various quantitative measures of complexity, give an accurate prediction of how much we should really be budgeting into. And maybe that would give a basis where managers would accept that this is a rule of thumb that's been well, you know, kind of proven in the field and has an analytical basis behind it. And therefore, in this satellite, I need 6 months, or I need 9 months, or whatever it is. Because right now, it is people with experience saying, you know, this is what I would do. And when it comes to spending real time and money and budgeting a program and giving up features you'd love to have on the satellite because, well, I need this money in test, I think a little backbone for that decision to say, Cold Star did the analysis for us, and we definitely need 9 months and $1 million to do these tests, would help us to be better managers, I think.
Right. Wow. You just said something that triggered me that we should have another talk on, which is it's one of the things that I really get clients to look at, is that the scope of what you're building and those features, and like what can you afford versus the complexity that you're building and the testing that's going to be required, right? And maybe you should cut some of those features. You've talked about that too. It's better to get something up there that flies and demonstrates a capability that you can build on, rather than trying to build some Frankenstein monster thing that is trying to do a whole bunch of things.
I mean, my rule of thumb is it's a one-bit world out there. You launch a satellite, could be the most complicated project you've ever done in your life. The boss calls you up. In the case of super large satellites, the boss might be the President of the United States. What are they going to ask you? Did it work or not? It's the one bit, evaluation.
Binary, right?
And you want to be able to give them the thumbs up. Everything's great, sir. And that answer is worth more than all the gigabits you're ever going to bring down from the satellite. So I will sacrifice almost anything. And scientists, of course, hate me, because they want those gigabits. But I will sacrifice a lot of gigabits to ensure that when we turn it on, it's going to work. And then everything else to me is a bonus after that.
Okay. Well, Rick, this has been fascinating. For folks who are interested in this kind of expertise and illumination of weird, don't know what you don't know stuff on projects like this, building spacecraft or satellites, come talk to us at Cold Star Tech. Dr. Rick Fleeter here is our technical engineering advisor, and he is available to look at this stuff. And I know a thing or two about program management and project management, that kind of thing. So, in those areas of potential blind spots, I think we have a chance of helping you not step on any landmines. Thanks for watching.